move this over to. I need to connect to the Zoom call at all there. Yeah. There we go. Perfect. Single button press. Okay. All right, great. Can everyone hear me okay? All right, excellent. So today I'm going to tell you about a few different nonlinear optical processes that we're studying in the Mabuchi and Fair labs. And these are ultra-fast processes that are happening in nanophotonic waveguides, specifically thin film lithium niobate. And a lot of the advances, a lot of these happening particularly in the Amir lab, with thin film lithium niobate has gotten people excited about all optical computing architectures. So for instance, here's a device that's proposed called a coherent SAT solver. And what this does is it takes a Boolean function and determines whether or not that can evaluate to true. And that's an NP hard problem that's well suited for these sort of all optical architectures. And a lot of these all optical computers, what they require is several nonlinear elements, in particular, optical memories, which involve things like amplifiers and gates to switch pulses in and out of cavities. And more specifically, I can give you sort of an animation of what this looks like. So imagine that I have a cavity, just this little ring resonator right here that a little red pulse is going around at, perhaps at the telecom wavelength. And there's an optical parametric amplifier. I'll talk more about those in a little bit that can amplify the pulse in the cavity. And in addition, there's another nonlinear stage, which can flip the frequency of the pulse in the cavity. So I can shift it from, say, the telecom to the visible. And that allows me to bypass a dichroic coupler right here, effectively switching the pulses in and out of the cavity. So these sort of nonlinear processes are what are going to inspire the processes I'm going to talk about today. So first, I'm going to tell you about supercontinuum generation through a cascaded second harmonic generation. This can be useful for making carrier envelope offset frequency measurements in order to get a stable pulse train to stabilize our tomes. Then I'm going to tell you about a gain-trapped optical parametric amplifier, which is a very robust way of doing broadband amplification in these thin film lithium niobate waveguides. And then I'm going to tell you about adiabatic frequency conversion and some of the advantages there, some extra degrees of dispersion engineering we can do, and how we can use that to make an all-optical gate. So starting off with the supercontinuum generation, I think probably a lot of people here are going to know what second harmonic generation is, but just to all get on the same page, I have a laser field with photons at a fundamental frequency omega. And second harmonic generation is mediated by the quadratic electric susceptibility of a material. What it does is it combines two photons into a third photon at twice the frequency. All right. So if at first I just shine my laser into this nonlinear medium, I'm going to find that I can't very efficiently generate photons at the second harmonic. So as second harmonic photons are generated, they're going to accumulate phase at a different rate as the fundamental. So as the fundamental is starting to generate new second harmonic photons, those can interfere destructively with each other, and I get these conversion cycles. So the way that we mitigate that is we need to somehow satisfy this phase matching condition. And by alternating the sign of the nonlinearity, we can actually achieve this. So right at the point where you have full destructive interference and we start back converting, we flip the sign of the nonlinearity, which flips the sign of the photons that are added to the second harmonic field, and we can get constructive interference and efficient conversion of our fundamental field to the second harmonic field. All right. And then inevitably, there's always some sort of non-idealities to our materials or interactions. And so eventually you'll have some back conversion that sets in, which is important for this cascaded second harmonic supercontinuum I'm going to talk about. All right. So now if I have two pulses in a material and they're at very different wavelengths, fundamental frequency omega and another one's at twice that frequency, I can't just send those into the material and expect that they're going to stay overlapped with each other for the whole propagation length through my waveguide. So what's going to happen is those two pulses are going to separate out. That's their group velocity mismatch. That's the rate at which they separate out from each other and no longer interact. And then I also have the group velocity dispersion, which is the rate that each pulse is going to spread out in time. And so you can see this gives me a very short interaction length, and I get a very weak nonlinear interaction. So what you're probably going to hear about several times at this series is dispersion engineering through the geometric waveguide dispersion. So the idea is here, for example, I have a thin film lithium niobate waveguide, and it's on sapphire. The dimensions here are roughly a micron, and I can change the geometry of this waveguide to change the dispersion of the waves propagating through it. I'm effectively changing how much of the field is overlapping with the thin film lithium niobate versus the substrate. So we can design this thing so that the group velocity between my fundamental and second harmonic is roughly 0. So here we're doubling a 2090 nanometer laser to 1045 nanometers. And then I can also get the group velocity dispersion roughly zeroed out. So when I'm in this limit, we call this quasi-static second harmonic generation. It's quasi-static because the pulses stay overlapped in time. And so only individual time bins will interact with each other. So I can treat the second harmonic generation as just almost a single mode thing that's happening in each individual time bin. And so what we see there is that we get these asynchronous conversion cycles between the fundamental field and the second harmonic field that depends on the local intensities of the fields in each time bin. Because it's asynchronous, that's going to lead to a whole bunch of these modulations across my electric field envelopes. And we can see that as these things propagate, those modulations grow, and those lead to the generation of new frequencies. So here we have some theoretical predictions of the experimental results for a fundamental field at 2090 nanometer, generating a 1 micron pulse. And you can see that the spectral broadening occurs as the pulses propagate. In this case, we're increasing the pulse energy, which increases the rate of the conversion cycles. All right. This is actually incredibly useful because we can use the interference that's happening between this fundamental and second harmonic field right here to measure the carrier envelope offset frequency here. So this is effectively the how far my frequency comb is shifted from 0. And if we're, say, generating a comb on a chip, we need to be able to measure this to stabilize that comb, and we want to do it with as little energy as possible. So here, this measurement was done at roughly 10 picojoules of energy. Typically, the scheme for making this measurement, it takes nanojoules of energy. You need to use some sort of supercontinuum broadening mechanism, so photonic crystal fiber, for instance. That creates a really broad spectrum. I send that into an interferometer where in one of the arms, I perform second harmonic generation. And then I recombine those two fields, and I measure the overlap of the corresponding frequencies there to measure the carrier envelope offset. So here we've gotten about 2 to 3 orders of magnitude more energy efficiency, and we can just do this on chip without building an interferometer. It's just a single traveling wave device that's doing the measurement. Okay. So in addition, when I take these pulses and I send it into my device, I'm not just getting the second harmonic out of this thing. So there's a whole cascading of mixing. These are extremely broadband pulses. And so and they're very, very intense. They're tightly confined, almost down to the wavelength of the, or in the case of the fundamental, down to the wavelength of the light that we're using. And so in this case, the coupling is so strong compared to the phase mismatch of all these other kind of parasitic processes that we still see them strongly occurring in the device. So to kind of get an idea of what's happening here, the intended process that we're performing phase matching for, that we've designed this quasi-phase matching structure, is taking these two fundamental photons and converting them to the second harmonic. But then the first and second can add together through a sum frequency process. Now, the same can happen for generating the fourth harmonic. We get the first and the third adding together to the fourth, but now there's two processes. The second can double to the fourth, and then so on. You get the first and fourth going to the fifth, and the second and third can also add to the fifth. And so the result is that you get this extremely broadband multi-octave supercontinuum out of this thing. And you can actually see this is 700 nanometers is about there, 400 here. So we can see the third, fourth, and fifth is actually in the visible region. And you can effectively see the spectrum being diffracted out of the chip. So here's the thin film lithium niobate on sapphire, this waveguide right here. You can see one of the waveguides is lit up. And the light is diffracting out, so our wavelengths are all separating. You can see the fundamental, the third harmonic is the red right here. You get a green fourth harmonic, and there's a little bit of a blue-violet fifth harmonic that we're seeing coming out of that device. All right. So now I'm going to tell you about our gain-trapped optical parametric amplifier. So the idea behind this device is we want to make a very efficient and robust amplifier on the chip that is somewhat insensitive to the light that we put into it. So here, optical parametric amplifiers work like this. I think a lot of people here also probably understand this process well, but just to make sure we're on the same page. You start with a really strong field at some pump frequency omega p, and the goal is to amplify some signal field omega s. And this is going to be a non-degenerate process. So the omega s is not half the frequency of the omega pump. And so to conserve energy, we create an auxiliary field, which is the idler field. All right. And these, the interaction starts with energy in the pump going to a signal seed. So we have a very small amount of energy in the signal we want to amplify. The pump converts to the signal, generating some idler in the process. And then the signal and idler, when they fully depleted the pump, are going to recombine through the reverse process of some frequency generation and regenerate the pump. So we get, no matter what, cyclic conversion cycles here. Okay, so we get these conversion back conversion processes. And in addition, there's a limitation on how much energy we can get into the signal. We often refer to that as the quantum defect limit. And that just refers to the fact that some of the energy is going into the idler. Now, with these optical parametric amplifiers, we often get well below the quantum defect limit. If you're trying to do some really high gain amplification, like even 40 dB of gain, let alone like 60 or 70 dB, I'm going to show you in a minute, you often only get about 2% of that energy, or a few percent, into your signal field. With this upper end, the 20% being more of like a power amplifier setup where you're only getting low gain. And the reason for this is these asynchronous conversion cycles. The same thing that I showed you in the quasi-static second harmonic generation can happen in this OPA, where I start with some bell-shaped pump pulse in time. The peak is going to convert to the signal first. Then we're going to reach full conversion of the pump to the signal, at which point the signal begins to back convert to the pump. So now I just have this kind of lobes off on the side here. And then the signal fully back converts, and then I get these modulations again. It's even more pronounced in this OPA process because of the Jacobi elliptic nature of the conversion. As you go to higher and higher gain, there's more and more time where you spend as the pump, and you don't have signal. So you just get these peaks like really far out instead of the fast modulations we saw in the SHG. Okay, and what's worse is that if I look at the energy efficiency of this thing, I don't want to have this nasty distorted looking signal in time that looks like two pulses. So if I want something that's actually relatively decently shaped, I have to cut the device at some length before the back conversion sets in. And that tends not to be the optimal point for the energy conversion efficiency. So even the maximum energy conversion efficiency happens when you have this really terrible looking shape. Okay, and Just a little further, some of the problems that you have to try to overcome here is that, again, we have dispersion in these devices. So the group velocity of the signal and the idler aren't going to by default match with the pump. In fact, we don't want it to match with the pump because we get the asynchronous conversion. And so these things are going to walk off and limit your conversion length so that you only get a small amount of gain. Okay, so now here's the idea. What you want to do is you want to take your pump, or sorry, your signal and your idler, and you want to dispersion engineer so that their group velocity is equal and opposite. So they're trying to travel in opposite directions in the pump frame relative to the pump. So when you do this, these guys effectively get gain trapped. So you form this kind of three-mode bound state, so to speak, where this signal and this idler are trying to escape the pump, but he's amplifying the inside edges faster than they can escape. And so they get stuck under the pump until it depletes. That gives us sort of an arbitrary interaction length. So these things are trapped. They're going to just keep propagating until they significantly deplete the pump. And then the beauty of this is that when the pump is depleted, the gain trap is broken, they just walk away. All right, and then in addition, you can see the spectra as the signal and the idler propagate here, and you don't get those really crazy broadenings or distortions. Do you have a question?
Yeah, it's a really dumb question for the micro. So like if we were to do that, like we typically do these sorts of things in just discrete modes, right?
Mm-hmm.
In principle, like we don't like you get the oscillation and stuff, but we don't necessarily like see this effect. I'm just trying to understand like where it comes from fundamentally. Like, is it because it's a broadband process that this like this? I mean,
the gain trapping in particular.
Before the clever gain trapping.
Oh yeah, okay.
The sort of original like quantum defect stuff and things like that. Like,
oh yeah.
Is it like what's the difference? I guess like in this system versus like like something where you just had a few discrete modes.
Mm-hmm.
Like is it somehow from the broadband? Is that where like where does that straight come from?
Yeah. I mean, so here you have like a continuum of temporal modes that make up all those modulations. But if you're in like just a few mode system, then you're not going to get coupling into this like continuum of modes, if that makes sense. Actually, maybe the next slide also where we can actually kind of do a modal decomposition of this in a way. So here we've defined some wave mixing equations for all of the different frequencies that are going to make up my signal and idler fields. We're working in an undepleted pump approximation, so this is the very early dynamics. And we could take into account, say, the pump shape. Here, I guess, if you had just a few mode system, you would only have, say, like 3 different fields that you're talking about here. And so there's not an opportunity for some like time-dependent modulations to arise because those modes just don't exist in your system. But here we have all of these different continuum modes. So like the eigenvalues, the eigenvectors of this system before we turn on the nonlinearity is just these CW lines that can all mix together and interfere with each other with different phases.
Can you remind us, like have millimeters as
x-axis? It is, I mean, so wavelength's about a micron. So 10 to the 3, I guess.
And you keep drawing the green and the orange at very different heights.
Yeah, let me go back.
Two-wave mixing should give same number of photons. So it's just like you showed your G0 photons over here.
So in the signal, you get the initial signal plus however many pump photons if it's fully efficient. Yeah. And then the idler is just the pump photons.
Yeah.
Yeah.
But it gains 57 dB.
Yeah, so this is for illustration purposes.
That's what I'm asking. So it's
yeah.
Not photon number, multiplied by the period.
Oh yeah, here's intensity. Yeah, so this isn't the photon flux. Yeah. Yeah.
Here's the sort of opposite direction.
It's just through the geometric waveguide dispersion. So you'll find solutions, especially when you have these really disparate wavelengths. So we're talking about like 1550 nanometers for the signal and something like 3.2 microns for the idler. And so they see very different dispersion, especially because the idler is much larger and can see more of the substrate. And so you will find places in your parameter spaces, you're changing the waveguide geometry in which you get group velocities that are equal and opposite. Yeah. Yeah, Evan.
Can I ask also like how robust this image, the HDM is?
Yeah. It's quite sensitive to the GVM. So definitely being able to fabricate these things with relatively good tolerance is fairly important. Yeah, it's not as sensitive maybe as some of the other schemes that we've come up with, but definitely, yeah, you want to get those relatively close. And the absolute value of the GVM also is important. If you make the GVM too slow, if these aren't walking away from each other too fast, then you do get significant back conversion to the pump. But if you make them walk like too quickly away, then the trapping is weakened. Yeah.
So are you working at energies where self-phase modulation is an issue? And if it is, can you actually just design it to mitigate that?
Yeah, so self-phase modulation, if you're pumping near like the damage threshold of the thin film lithium niobate, you'll definitely start to see some self-phase modulation effects. It's not going to be super strong, but I don't think there's like a cascaded nonlinear phase shift or anything that we're developing here. So the other process, the cascaded SHG, if you were to take that into the really phase mismatched limit, then you could conceive of a device where the cascading second harmonic provides a nonlinear phase shift that then cancels the type 3 self-phase modulation. Yeah. Here.
What's the relation between the shape of the incoming signal?
Yeah, that's actually a really good question. I mean, so these are actual simulations, and I think you get some broadening, I want to say. Like you can kind of see as this thing comes in, because there's like this leakage that's happening, but I don't know the exact like analytic form that takes, but it's probably something like a convolution between some kernel related to the pump shape. Yeah. Cool. Was there any other? Yeah.
In terms of like, sort of original stuff that's happening, like how important is like, I guess bandwidth of the pulse relative to, or I guess spatial extent of the pulse versus like the spatial extent over which you should be having this. For example, you had it happen within one wavelength, that like change the quantum defect limit or something like that, or
yeah, so the quantum defect limit is just a hard limit based on the frequencies that you're using. It's basically just a quantum efficiency. It's that for every photon that I make in the signal, I have to make a photon in the idler, which is what Michael, I think, was referring to. But so if I look at the photon fluxes, there is like a max amount of pump photons, or the amount of photons that I can add to the signal from the pump is equal to the initial number of pump photons that I have. But that same amount of pump photons are going into the idler. Yeah, and then their relative frequencies set the quantum defect. Yeah. So if you wanted to be in a regime where the quantum defect limit is not hurting you too much, then you want to be in this extremely non-degenerate regime where the pump is close to the signal. And then the energy of the idler photons is extremely small. Yeah. All right.
Determining the frequency of the idler here?
I'm sorry, what's determining? It's the energy conservation with the pump. So it's it's effectively what we choose it to be. So whatever field that we're trying to amplify. So this isn't being amplified out of noise. It's just we send in some signal field that's it could be like a CW wave, as I'll show in a minute, or it could be some pulse that has some structure or some bandwidth to it. Yeah, but it's whatever laser that we're sending into the device. And you're going to explicitly design a quasi-phase matching structure, like I showed in the beginning, that satisfies the phase matching constraint between these three different fields right here.
What determines
It's also the laser that so I have basically two lasers that I'm combining into a, I think I might have a picture here. Yeah, so a really common laser wavelength that we use for the pump is these 1 micron, so 1045, 1030, 1064 nanometer lasers. And the signal oftentimes is, say, like a telecom signal. And so you just want to choose, I mean, lithium niobate is transparent to these wavelengths. I could choose any pump wavelength. I could have used like a 1300 laser, but it's hard to find, you know, high energy pulse lasers at that wavelength. Yeah, and then I just have to design my dispersion around these wavelengths that I have in my lab. And then I choose QPM periods that explicitly phase match these wavelengths. Yeah. All right. I think this is good, filling in some gaps I probably should have included in the background here. Yeah.
So I guess in principle, like one could do all this W as well, but by having the ultra fastness, you can get a lot more energy, which helps handle all these processes. So
yeah.
That's good. And so then that's why I should have my pump in the time domain. So I basically want to have time domain. Although it's kind of in the middle. It's narrow band.
Yeah.
But it's a sharp pulse.
Yeah, exactly. At least when you're talking about lots of photons, a very short pump pulse, which is going to give you a very broad spectrum to your pump, is going to be ideal for enhancing the nonlinear interaction because it goes as the peak power. But the challenge is, can I phase match that whole bandwidth? Am I going to get like interpulse mixing that creates a lot of parasitic stuff in my pump pulse? For instance, when you make your pump really strong, it starts to see strong second harmonic generation. And so that second harmonic generation can start to deplete your pump, or it can interfere with the nonlinear processes. You might get like intrapulse mixing where the different frequencies in the pump start adding and subtracting from each other and creating all sorts of craziness. So there's a lot that can go on. So you're, yeah.
Do you think about it in the time domain or the frequency domain, or do you have some hybrid?
You kind of have to think about it going back and forth in both.
I mean, having the intuition is really good, but mathematically, is it one or the other, or some?
We're often kind of thinking of it in both, or maybe even like kind of a Wigner transform type thing, where we're looking at each frequency as a function of time. Yeah. And how those are distributed, especially when you're talking about the dispersion, that it can effectively rearrange where each frequency is in time. And then you need, if certain frequencies are overlapping in time, but others aren't overlapping in time, then only the ones overlapping in time will mix together. So you can change the bandwidth of your interaction just by not having certain frequencies overlapping with other frequencies in time between your two pulses. Yeah.
Can I add a comment?
Oh yeah, go ahead.
As someone who like works in microwaves, I think you talked about it a little bit, but something that's really important on the optics side is the dispersion.
Yeah.
And like a lot of times in the microwave systems, we're using energy conservation to pick out processes, so resonances. But in optics, most of the time you're actually using momentum conservation.
Yeah, that's right.
To pick out processes.
Yeah.
And so engineering that dispersion is like the analog of the engineering the resonances. So a lot of the efforts spent on.
Yeah. Yeah, I think that's a really great point. Like, I think a lot of times in the microwave stuff, you're thinking about these kind of T-propagating frames, and in the these photonics, like or a traveling wave, like you have a resonator, and you're considering the field at all points in the resonator evolving as a function of time. Whereas in these devices, we're often describing the pulse as having some envelope in time that's propagating in Z. So the time is a description of the extent of the pulse, whereas Z is the actual parameter that is proportional to the evolution of the system instead of time. Yeah. And so we're often talking about things in terms of like momentum conservation, whereas I think in a lot of the resonator pictures, things are, or sorry, the other way around. Momentum conservation in the resonators and energy conservation. Yeah. 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 So here our omegas are fixed and our delta Ks are what we're engineering, or the Ks themselves. Yeah. 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 And when these things get very, very broadband too, like you can only dispersion engineer so much. You start to see very complicated, like higher order dispersion effects, or you might have mode crossings that your bandwidth is extending across, which does very complicated things. And yeah. All right. Any other questions on this? I think this is Hopefully this filled in some gaps. All right. So let me go back to this slide real quick. So we have these wave mixing equations that describe how all the frequencies of my signal and idler are mixing with my pump. This takes into account the pump shape and the dispersion, the k vectors of each of my frequencies that are involved. When the nonlinearity is off, the eigen vectors of this thing are just the CW lines at each frequency. But as we start to increase the pump energy in the system that we're using to amplify, we start to see these broadband modes form. And they form very, very discretely. And we can plot the gain of each of these different modes. And what we see is that this broadband mode here gets amplified, whereas all these continuum modes, all these discrete CW lines actually get suppressed. And that's really cool because what that means is that we get this qualitatively different behavior than a normal OPA. So normally in an OPA, if I take my seed frequencies, so these are CW lasers at different choices of seed wavelength, and I amplify them, the spectrum is going to shift as I shift the seed that I'm amplifying. But if I look at this gain trapped OPA, if I tune the frequency that I'm seeding, it doesn't actually change the shape of the amplified field. So in all these cases, I get these broadband spectra, which are these single modes that form in this gain trapped OPA. And we can see then here's some experimental results showing exactly that, where it's effectively like there's a single mode that is amplified regardless of what the seed frequency is. So this makes it kind of robust to whatever the seed pulse shape is and bandwidth and all that. All right, and so in this device, then we're able to do 70 dB of gains. This is an extremely high power amplifier or high gain amplifier. And it's with 50% conversion efficiency. So remember, at the beginning, I said with these types of amplifiers, you're often just getting a few percent conversion efficiency. So they're able to increase the efficiency by about an order of magnitude for this extremely high gain amplifier. Any more questions or things I should clarify? All right. So the next thing we're going to talk about is adiabatic frequency conversion. And this is in analog to the Landau-Zener theory that a lot of people might be familiar with, like rapid adiabatic passage. Instead of doing it with, say, like a two-level system in a magnetic field, we're going to be doing it with these waveguides for very broadband pulses. So there's been actually quite a bit of work done on this here at Stanford, and then also a few other places, including Cornell, where I did my PhD. And so people have studied how you can use these things to make extremely broadband optical parametric amplifiers, but also how you can use it to make three-wave mixtures that do sum and difference frequency generation, where the number of photons in the input field is preserved with the number of photons in the output field. I'll describe a little bit more how that interaction works. But yeah, so these have been used for generating light with multi-octave bandwidth, so you can do this all over the transparency window of your material. You can use the structure of your quasi-phase matching to engineer the dispersion that your pulses see. So it's an extra degree of freedom for dispersion engineering. It's also sort of linearizing the nonlinear conversion and can preserve the amplitude and phase information of your pulses. And then it also enables unidirectional conversion. So if you're familiar with the rapid adiabatic passage, I'll show some plots of that. Okay, so here's the idea. What I'm calling some frequency generation is this case where I have a intermediate field that has many, many photons. This is going to be my gate field. It's intermediate in frequency. I have some higher frequency signal that's my input field. And when these mix together, I am converting the photons one-to-one to this output frequency field. So here we're doing this, some frequency process where I'm up converting an input field to an output field. And it's effectively just a translation of the frequency. So each frequency that I input here just gets linearly translated to a new output frequency with the same kind of delta omega between the different frequencies. And then I can extend this to a whole pulse where I'm mixing this strong narrowband gate field. I'm really just shifting the carrier frequency of this thing, right? So let's go ahead and do this process. So I'm going to pull my material. So this is satisfying that phase matching condition, the momentum conservation effectively. And I'm gonna take some omega input field and mix that with my gate. So photons from these two fields are gonna mix together to give me my output field. And what I see is that I can get full conversion at this central frequency right here. So these are the output wavelengths. The input wavelengths are around telecom. So I get these full conversion cycles. They look like Rabi oscillations. But as I detune away from that central frequency, my conversion cycles speed up and decrease in amplitude. So just like we would expect from like a detuned Rabi oscillation, right? And this is not great if I want to do broadband nonlinear optics, right? I need to have a transfer function that takes this entire input pulse shape and transfers it to my output pulse, preserving the shape in the phase. All right, in addition, if I want to maximize the conversion, I can cut the crystal here. And so that gives me the largest efficiency for the central wavelength, but it's a very narrow bandwidth. And if I cut the crystal earlier, I could get a broader bandwidth, but the efficiency goes down. So we can get around this bandwidth efficiency trade-off by chirping the device. So what I mean by chirping is that we're going to sweep this quasi-phase matching period so that this phase matching condition is satisfied for all of the different input frequencies that make up my pulse. And so then what I see is that each of the input frequencies in red, or input wavelengths here in red, are at some position converted to my output frequencies in blue. And that corresponds to where this phase matching condition is satisfied in each of these, or within this device. So for instance, the 640 nanometers is generated early on in the device, where its phase mismatch is 0 here. And the 600 nanometers is generated later in the device, where its phase matching occurs. Okay. All right, and so I can look at the lineouts here, and this is our usual rapid adiabatic passage. And then we can see this for each of the different wavelengths here. The conversion is fairly local, so it happens very quickly over a narrow regime of the pulse. And I can effectively just make this device longer if I want to phase match more wavelengths, or I can chirp I can sweep this thing faster so that I can hit more phase matching conditions. However, if I want high efficiency, I need the sweep rate, the rate that I change delta K here, to be small compared to my pump intensity. And so it's kind of like an upper limit, however much energy I can get into the device, I can't exceed. Yeah. Yeah, so it's actually, that is one of the advantages of this, is that it's fairly robust in that you just need to go through that phase matching condition, but it doesn't matter the exact trajectory. So if I have some like variations along the sides of my waveguide or the top of the waveguide, that is going to change where the wavelength is converted. And I'll show later that that actually could change the dispersion, but it won't necessarily change the fact that the wavelength does get converted efficiently. Yeah. So if you have a device, maybe it's you want to do some single mode mixing or some CW mixing, and you just have one phase matching condition you want to satisfy, you can chirp that device just a little bit to give yourself a little bit more room to convert somewhere in the device. But the expense is that you have to pump it a little bit harder. Yeah. Yeah, I mean, so you are still, it's actually this couple mode thing. So I have like an avoided crossing. And I want to start this thing at a really, really large phase mismatch. And then as I tune the phase mismatch, I'm moving along this avoided crossing curve. There's a point of optimal coupling, at which point I very quickly convert here. But there's going to be some regions that are near the perfect phase matching condition right here, where I'm still fairly strongly coupled to my other field. Like the input and output field are fairly strongly coupled. So I get some conversion back conversion cycles. Yeah. And if you pump too hard, those can get really large, and that can induce some nonlinear phase shifts and do some complicated things. Yeah,
A conventional ASFG, even if you phase match it, I believe back and forth. So I was wondering why it saturates here.
Yeah, so this is the whole Landau-Zener rapid adiabatic passage kind of stuff. Yeah. We can, yeah, it requires that you go through zero, switching the sign here, but it's effectively just these trajectories across the, or you're adiabatically evolving the eigenstates of your system. So if I start in an eigenstate of the system, which when my delta K is really, really large, these things aren't nonlinearly coupled. So I'm starting in my omega input field, but as I turn on the nonlinear coupling, my eigenstates start to become a superposition of the input field and the output field. As long as I do that slowly, my input field stays in the eigenstate. And so it goes into that superposition here. As I continue to evolve the faceless match to the other side, then I move my eigenstate into the opposite of the initial eigenstate, which is my output field.
So you're like not phase matching the previous frequencies, so they never come back.
Yeah, I guess. Yeah. Yeah, that's a really good question. So in this case, we're doing the up conversion. So your pump is going to be generating some SPDC if, like wherever I guess it gets phase matched, but that's going to be at like a lower frequency, whereas we're kind of up converting the signal to a higher frequency to avoid any SPDC that might be generated. The SPDC efficiency, if it's phase matched here, is going to be lower, but it's probably going to be more broadband. Yeah. Okay. Cool. All right. Great questions. Okay. So yeah, in any case, each of these things follow these unidirectional trajectories. This was also shown about a little over 10 years ago that it indeed follows the Landau-Zener trajectories. There's a lot of questions early on in this field, whether you would still have the conversion cycles in this or not. But what's being shown here is that if you, this is effectively integrating the energy of the pulses that are being converted. And it shows that as you turn up the pump intensity, the conversion efficiency actually just saturates at 100%. So instead of going through back conversion cycles, you just get all your photons from the input field shifted over to the output field, just shifting the carrier frequency. Let's see, how am I doing on time here? Okay, I'm doing pretty well. Okay, so there was some work showing that that this device does indeed give a linear transfer in phase. I won't dwell on this too long, but the point is that in this experiment, it was found that the device actually imparts a really crazy dispersion on this thing. So it takes all of the frequencies that are in your input pulse, and it kind of just scrambled them around in time. All right, so the output pulse you get has a very complicated relationship between where the frequencies are in time relative to the input pulse. And so the grad student that worked on this, he had to build a really complicated dispersion management scheme. So it involved all these things, prisms, which if you don't know, it's a prism with a gradient etched into the backside of it. He had to use this bulk silicon compressor, but the main thing is he had to use this dazzler. Here I'm reporting these numbers here. So remember, group delay dispersion is the same effectively as group velocity dispersion. It's how much your pulses stretch out. Third order dispersion is how much your frequencies follow a parabola in time. So my red, green, blue in time kind of thing. But this actually is not even a good approximation for what the dazzler was doing. So this is a pulse shaper that allows me to programmatically move my frequencies in time. And what he had to do is just spline together 3 different high order polynomials to even get this thing to work out. So obviously that's a problem if I have a waveguide and I use one of these devices. It's just going to scramble up my pulses in time. And I don't have a lot of good ways to do pulse shaping or dispersion management on a chip. So this thing really kind of needs to, compensate its own dispersion. And so fortunately, there was some great work first done in Fair's group here by Charbonneau-Lefort, where he showed that the idler field, basically the unseated wave of an optical parametric amplifier, picks up a phase from the design, the chirp rate effectively, or your chirp design here. So what we can do is we can actually design our gratings to impart some phase to the one of our optical fields. And I'll show how that works. All right. So in our case where we're doing some frequency generation, our input field, input wavelengths are all of these red wavelengths here. I can write down what the total group delay for each of my frequencies is. So that's how much time did it take my input wavelength to go through this device, convert to the output wavelength, and then make it to the end of the device. And that's given by this expression here. It's the total time it took each wavelength to get to this conversion position, plus the total time it took each output wavelength to get to the end of the device. All right, so it's really simple. The reason we can approximate this like this is that we have this rapid adiabatic passage where we have this really sharp transition from the input field to the output field. So we can approximate it as just being the time it spends as an input field versus the time it spends as an output field. Okay, so this now gives us an equation for where our frequencies are in time at the output of our device as a function of where they converted in the device. All right. So now what we can do is we can design the period of our grading. So yeah, how fast our grading is oscillating between plus and minus nonlinearity based on where we want each frequency to be phase matched at the position that we're going to design to give us a good output profile in time. All right, so all this is to say that we can just say I want like a flat, I want all my frequencies to line up in time. I want a compressed pulse. I don't want it to be scrambled. So I just set this T out to be 0. That means that all the frequencies are at the same time. I plug this 0 into this equation and solve for Z. And then this tells me exactly how I should design my grading. Okay. So for instance, we've done an experiment with this where I have a broadband near IR input pulse. In this case, I'm going to down convert it to the mid-infrared. And the way the device works is that I send my input near infrared pulse in, it stretches out in time, and then each wavelength gets converted at a different position, such that at the end of the device, the pulse has recompressed. So my device is acting like a stretcher, a converter, and a compressor, all in the same thing. So it's doing its own intrinsic dispersion management to keep my pulses together. Okay, and in this device, we used 11 femtosecond near IR input fields, and we were able to get out compressed 11.6 femtosecond mid-IR field. So here's a retrieval of the electric field envelopes and then the phases of those pulses as well. And then you can see the output spectrum there is spanning over about like an octave. So it's like about 2 microns to 4 microns. So this is an extremely large bandwidth that we're converting. If we had just done periodic polling instead of this adiabatic polling, we would have been talking about just a narrow strip that we would have been able to convert over here, only just a few handfuls or tens of nanometers versus 2 microns. And in addition to that, we can dramatically simplify the dispersion compensation by eliminating it altogether. Okay, so then in the theme of all this dispersion stuff, we also want to, if we want to build one of these devices in a waveguide, we want to do some dispersion engineering. And so the thing that we're actually going to do here, we're not going to make all of the pulses overlap with each other. It's actually really hard to do the dispersion engineering out at these visible wavelengths. So here we're taking our telecom 1550 pulse, we're mixing it with a 1 micron gate, and we're getting something like a 620 nanometer pulse coming out of this thing. Okay, so what we're going to do though is we're going to try to make the gate pulse and the input quasi-static. So we're making it so these guys stay overlapped and they don't spread out as they propagate through the device. And then we're going to generate our upconverted field, and we're going to use the quasi-phase matching structure to engineer the dispersion of that output field. All right. So this largely is going to solve the problem of working with short wavelengths in these devices where it's hard to use geometric dispersion engineering. And then it's also going to allow us to work with extremely large bandwidths that correspond to about 40 femtosecond pulses. Okay, so in this device, we're designing it to take a 40 femtosecond telecom pulse, about 100 femtojoules. It's going to mix with a up to 5 picojoule 1 micron pulse, and then what we're going to get out is going to be an output pulse at about 625 nanometers with the same input pulse energy roughly in a 40 femtosecond pulse duration. Now, if I want to design this so that I have a compressed input to get a compressed output, I'm actually using only just a very small region of the device to do the conversion. And by the equation that I showed earlier, that the amount of pump intensity that I need is inversely proportional to the chirp rate. I want to actually chirp this thing as slowly as possible. So I want to extend the conversion over as much of the device as possible to reduce the amount of pump energy that I need to convert this thing. So what I'm going to do instead is make a design that imparts about 6,000 femtoseconds squared. So that chirps me out to a 200 femtosecond pulse from 40 femtoseconds, but with a dispersion that has a sign that is easy to compensate. So in the visible, it's easy to compensate in anomalous dispersion, this negative dispersion with a normal dispersion. Okay. So now if I look at some propagation data here, these are all just simulations, and I have a telecom input. You can see that each of the frequencies convert at different positions. And then I generate this signal output at 625 nanometers here, which is stretched out to about 250 femtoseconds. If I de-chirp that by applying just pure 600 or 6,000 femtoseconds squared of GVD, we can see that here's the input pulse, here's the output pulse. I got the full 40 femtoseconds through, so I've converted over the entire bandwidth without adding significant distortions to the pulse. And then I can look at how this thing behaves as I change the energy of the gate pulse. So as I increase the gate pulse energy, we can see that we increase the conversion efficiency until this thing saturates. And so what I'm doing is I'm changing the superposition of input pulse and output pulse effectively. So that in this device,